Hello.
Go ahead, Pedro.
Oh, okay. So we're ready?
Yes, it's recording.
Oh, okay. So welcome. It's my great pleasure to introduce Filip Ilievski. He's been working in our group for a little bit of over a year on the machine Commonsense project. And now we're interviewing him to apply for the permanent computer scientist position. And so we're very happy to have him give a talk. Get started. And I'll be listening while I drive.
Okay. Thank you, Pedro. Right. Yeah, it's a big pleasure that for me to actually be able to talk to all of you about the research that I've been doing at ISI over the last year or so. So I joined ISI in December 2019, which was a little bit pre-COVID. So I didn't really have much chance to talk with most of the people in the audience in person. So I'm happy to have the opportunity to actually share what I've been doing and where I intend to go with this in the coming years. So the topic of the talk today will be how to build agents with common sense knowledge. If we think about AI in the future, so let's say AI in 2050, we often have these futuristic ideas about what the AI will do. So it will manipulate information, like complex sort of information from different places for us. It will be in our household, so it will help us clean, it will help us maybe with cooking, it will collaborate with us on these aspects. It will be, a big project is the self-driving cars. So basically we intend to build these agents that will be able to drive on their own, to figure out how far the other participants are in the traffic, but also sort of predict the intention of the other things. So have these very complex models of what is going on around us. And finally, because AI is starting to get able to be able to create sort of music these days. So if you've seen all the newspapers about GPT, whatever, creating music. Why not? Maybe in 2050 we'll have AI sort of playing, in our living room for us, like AI bands playing for us, which would be, great, because we haven't really seen a lot of live music recently. So this seems like a good thing to aim for. Okay, so why are we not in 2050? So if we think about all of these nice things that we want to get towards, so why are we not there? And one of the big reasons why is common sense. So this is a presentation by Oren Etzioni from AI2 last year at USC, just pre-COVID, where he was talking about how one of the key sort of obstacles towards achieving general AI is the lack of common sense. So here he gives an example of an image where the AI thinks that that bubble of water behind the duck is actually a car. So obviously, if we want to build self-driving cars or other intelligent agents, doing this sort of silly mistakes is a serious obstacle. So before I sort of introduce the technical part of this, let me talk a little bit about what I mean by common sense. Common sense, according to Ernst Davis, which is one of the leading cognitive scientists and people that work on common sense knowledge these days, is the common knowledge about the world that is possessed by every school child, and the methods for using this knowledge to basically make obvious inferences. So if you look into this definition, it sort of talks about two things. The first half of the definition talks about the knowledge that is sort of the key to common sense. The second part of the definition talks about how to make inferences, how to reason over this knowledge. So it turns out that this common sense knowledge is something that people have been interested about a lot in AI. So so let's say here in 1989, John McCarthy, another pioneer of common sense, gave a definition of common sense knowledge as sort of a union of basic facts about events, about beliefs, about desires, about objects and their properties. So we see that common sense knowledge is this sort of, it's quite a broad set of knowledge that we think about when we think about common sense knowledge. All right, so can we make that a little bit more concrete? So here you see three key sort of aspects of common sense that if you look through the literature over the last, what is it, like 60 years or so, we see that people have typically talked about these three things. The first one is intuitive physics. Second one is common sense psychology or intuitive psychology. And then the third one is talking about common facts. Here in the bottom, I listed some of the key works and key people that have been working on this, including John McCarthy, Patrick Hayes, Ken Forbes, Jerry Hobbs, and Ernst Davis. So I think people have been really thinking about these aspects really a lot. So we have 60 years of history, and really it's rich with work on all of these aspects. So let me get a bit deeper here and talk a little bit more about each of these. So if we talk about intuitive, or it's also called naive physics, what do we really mean? Here we mean the knowledge about how the physical world works according to an untrained human perception. So basically this means how the physical works, not according to a physicist, but basically by an average Joe on the street. So what really goes into this? Well, things like, for example, if something goes up, it must come down, or an object can be in one of these two sort of states. It can either be at rest or it can be moving, but it can't be both and it can't be neither. So this is sort of very crisp way to look into this. And people have been trying to approach this from different ways. One idea that people have been working on is this idea of devising microworlds about these physics phenomena. For example, here you see sort of an exempt from that shows how you can design the interaction between a blade and a target and what really happens over time. In terms of common sense psychology, here I would like to briefly talk about the work by Gordon and Hobbs. So there is a really comprehensive book on these that's published in 2017 on formal theory of common sense psychology. So what do we really mean here? It's typical when we talk about common sense psychology, we talk about understanding human thought and actions in situations. And there are a lot of things that fall into this. So we talk about goals, we talk about plans, beliefs, expectations, desires, emotions. So all of these things that we relate to kind of common sense or naive psychology. And the way in which Gordon and Hobbs have been thinking about this is in terms of axioms. So basically, if you want to say that something being near a person is an enabling condition for the person to perceive it. So this sort of means that if something is near a person, that the person can perceive it, then you can encode this with this sort of logical formulation. And then the third segment of these aspects of common sense is the common facts. So here, what we mean by common facts is basically things that an average person, knowledge that an average person possesses. So knowledge about facts that the average person knows. Things like, knives are used for cutting, or an embassy is a type of government building, and so on. And this sort of knowledge has been mostly captured by different common sense knowledge sources. The first one that always comes to mind, I guess, is Psych, the work by Doug Lennart. In the more recent years, in the 21st century, we have a bunch of other common sense knowledge bases, including ConceptNet, but also many others that I will talk more about later in my talk. Okay, so if we go back to this, so I talked a little bit in depth about these three aspects of common sense. but the essence of these, of basically being commonsensical, being a commonsensical agent, is that you have to know how to do all of these things. So it's not that you basically know only how to do physics and you have no clue about psychology. But if we think about reasonable sort of commonsensical agents, we think about basically an agent that can do all of these sort of at the same time. But the agent should also know when each of them matters. So if you have a situation in which perhaps you should use a specific kind of intuitive physics, you should use that one, or maybe you should combine it with some common facts that you know. So this is sort of the key to being commonsensical. So with all this sort of in mind, let me introduce the key research goal that I have been thinking about. So the research goal is, how do we build a natural language agent that can perform well on all of these different aspects of common sense? All right, so let's get a little bit more technical here. If we think about, if you think about like the more recent history of AI, so let's say the last 3, 4, 5 years, what you see a lot is a lot of neural architectures, and especially if we talk about sort of natural language agents, the first thing that comes to mind is, neural language models, or especially transformer neural language models. So I guess many of the people in the audience are actually familiar with them, but let me give a little, just a brief recap of how these actually work. So these transformer language models are typically trained on 2 tasks. The first task is called masked language modeling, where the goal is to take a sentence that has a missing a token or multiple missing tokens, and make a prediction what could that token be. For example, if we have this one, my dog is masked, the system has to figure out that one possible answer to that is my dog is hairy, or one possible extension. The other task that language models have been trained on is the task of next sentence prediction. So what is meant here is that you have essentially 2 sentences, sentence A and sentence B. For example, the man to the store, and then sentence B would be penguin are flightless birds. So basically, the system has to say whether these 2 sentences sort of fit together well, or to be a bit more precise, whether sentence 2 follows sentence A, in a reasonable, in a sensible way. Okay, so how do we do this? How do we really do the pre-training here? What is really happening is that we have, let's say if we talk about the second task of next sentence prediction, what we have is we would have like sentence A, a sentence B, which are still masked, so they still can have some words missing in them. And what we do is we basically sort of run these through the transformer. So one transformer that has sort of started the transformer saga is BERT. So let's go with that one. So essentially, let's say we have these 2 sentences. We put them through BERT, and then BERT has to figure out what are the masked tokens that we're talking about, but also what is the next, whether the second sentence is a continuation of the first one. And along this process, basically, BERT is being trained on really a huge number of data. So we're talking about sort of billions of tokens. And then BERT is able to train the weights of the network that it has inside. So it's sort of an encoder-decoder network. And in that way, we are sort of having this thing that collectively we call a BERT model that we can then go ahead and apply on all sorts of tasks. Okay, so here's where it gets a bit more interesting. It turns out that if you take something like BERT that you have pre-trained, you can really fine-tune it on a wide range of tasks, which include question answering, include other NLP tasks, and you can see here that the way in which we do this is by what we call fine-tuning, which is essentially training BERT a little bit more, but now with data that comes from the task itself. And the interesting thing is that people have been trying to do this also for common sense. So this is where, this is basically what has been happening in the last few years. So if you can do this for question answering, why can't you do it for common sense? And essentially, we've seen a lot of these systems that, would take a question and an answer sort of, will run it through BERT, and then BERT will be able to say, okay, how to break a window, you can use Metal's tool. And then BERT will eventually use its model with the fine tuning that it has on this data, and then make a prediction. Do I think that this is a reasonable thing or not? And once we figure out how to do that, let's say on physical IQA, how to do this for physical sort of question answers, we can expand this idea to, social reasoning or whatever, numeric reasoning, all sorts of other tasks that we are interested in. And, perhaps somewhat surprisingly, perhaps not, we have seen this sort of strategy working extremely well. So if the human accuracy on, let's say, physical IQA here is, 94, 95%, then we can have a language model perform, a few percent worse than humans, so like 90% or so. And similarly for social IQA, this is a data set of social reasoning. If human performance is 88, language models can get, again, fairly close, a few percent closer. So, to be fair, the ones that are topping the leaderboards right now are not exactly always transformers, but essentially, in these cases, we see that they tend to perform extremely well, and they always get close to what humans do. Now, what is the problem with all this? Why? So I've been talking about how this all can be done, and it seems like there is this very elegant solution of basically taking a language model, fine tuning it with whatever data you want to train it on, to basically be able to perform well on, and then sort of performing very well. So why is this not optimal? Well, the problem with this is that, but with this strategy, we are building sort of one BERT per data set. So we are building a BERT instance for social IQA. We are building a BERT instance on, Commonsense, which is sort of numeric reasoning, for physical reasoning, and so on. And all of these BERTs are sort of, independent of each other after the fine tuning. So this means that essentially we are able in this way to solve any data set, which is, great from an engineering perspective. But from a perspective of building of sort of like a common sense agent that can do all sorts of things, this strategy will essentially just not work. So this is really what happens. So if we take something like Roberta, which is, sort of BERT ++ model, sort of an improved version of BERT, and if you just run Roberta without any fine tuning on these 5 tasks, we get performance, let's say between 45 and 67%, something like that. If we fine tune Roberta on each of these tasks, we get big boosts. You can see that the boosts are, sometimes as much as double or 20, 30%, really very high. But again, what this does is basically it gives us this sort of different BERTs, and each dataset has its own BERT. And we see here that this adaptation, this fine tuning, is really crucial to get good performance. So without it, we are back to this range of much lower accuracy of the language model. So the question that I would be pursuing is essentially, can we do this now? Can we do the same thing that we are able to do with the fine tuning, but then do this without relying on dataset specific training data, but rather being able to somehow pre-train the models and have a model that can deal with all of them, with all of the datasets. So the idea that we've been pursuing is the idea of using common sense knowledge sources. So if we forget about training data, what else is there? Well, there is a lot of other useful data out there on the web, and one segment of that is the segment of common sense knowledge. So sort of structured or semi-structured knowledge that people have been very carefully or somewhat carefully, depending on the approach, collecting over time. And there is a lot of this knowledge out there. So can we actually just use that one and see what happens? So this is an example to show the intuition behind this. So if we have a question, and this question comes from one of the data sets that we are working with. Sorry, this is rather, people call this a question. It's actually rather, I think a better way to call it is essentially just a multiple choice sort of task, because the question is really implicit. In this task, what we have is essentially a stage, and then the stage has a woman that takes a seat at the piano. And then the task of the system is to figure out what is a reasonable, commonsensical continuation. So if you imagine this as a scene, what makes sense as a follow-up scene? And the correct answer is that she, sets her fingers on the keys, nervously. And if you look into the connection between the question and the answer, it's a sort of it's not an obvious question, because you have to know a lot of things in order to connect the dots. You have to know that pianos have keys, and that that you play piano by setting your fingers on the keys, and that this sort of entails a performance, and that when people perform, people are nervous. So really a lot of things. So what happens is that if we look into these existing common sense knowledge sources out there, we are able to find a lot of this evidence, sort of in different places. So basically, if we ask ConceptNet, okay, so what do you know about these things? ConceptNet says, well, pianos have keys, and if you do that, you can perform music in that way. If you go to WordNet tells you that pianos are played by pressing keys, so that's a rather more specific description of how pianos are, used to create music. ATOMIC says that, in order to play a piano, you first have to sit at it, be on a stage, and reach for the keys. So this is sort of a bit more, more specific, more causal sort of explanation of that basically sitting comes before actually be playing. And then if you ask Visual Genome, which is yet another source, we see that, the person can play a piano while sitting and, with his hands on the keyboard. So by doing all of this, we are able to kind of to find connections between what we have in the question here and what we have in the correct answer. Whereas we are able to also find some evidence that some of the other answers are sort of not really correct. So one such case is, for example, FrameNet, that tells us, that if we have a performance frame, there is a performer and there is an audience, but these are two different entities. So that, for example, allows us to say, we know that woman is not really in the crowd because the audience is in the crowd, and the woman is actually the performer. So hopefully this gives you an idea of where we are, why we think that this would be a reasonable approach to pursue. Okay, so let's talk a little bit about how that really happens. So I showed you that we have language models that have this tremendous power to learn things. On the other hand, we have common sense knowledge that is sort of found in a bunch of different places that seems useful, but it's sort of scattered. So how do we really do this combination of the two worlds? And so one way to do this, so basically we start thinking about this by first looking into what sort of common sense knowledge sources we have out there. And it turns out that there is a big pile of common sense knowledge sources, but they're largely heterogeneous. So they differ in terms of their representation. Some are symbolic, some are expressed in natural language, other are even like neural knowledge bases. They have been created in different ways. They have different knowledge types and topics and so on. So the first thing that we did was, okay, so we thought, can we go out there, pick some of the key knowledge sources that seem most promising and integrate them into a single common sense knowledge graph. So I will not talk about the details about how we did this here, but the main thing is that, because of this heterogeneity, this consolidation is actually quite challenging. It is, however, quite rewarding, because if we do that, then we are able to get this consolidated knowledge that gives us some of these pieces that I showed before, that we can basically put them sort of together. And then we know that, catching frisbee is fun for dogs, and we know that if a person throws frisbee, then others have to catch it, and catching and throwing is an antonyms, whatever. So basically we can get this sort of consolidated knowledge that combines nodes from different places. So this is the key to our method. So this has been published this year at AAAI. What we do basically is we take our consolidated knowledge graph, CSKG, and what we do is we say, okay, can we take the knowledge graph and sort of fake the training data with it? So we take the knowledge graph, we use the structure of it, the different paths that we find, and the edge patterns and whatever. So we take this and we try to see, can we extract, first of all, sort of useful information from the graph. So this would be one triple, losing weight is used for being healthier. We can lexicalize it to make it sort of human readable. And then the next part is, how do we really get things that will distract the system? So I'm talking about this sort of multiple choice tasks. We basically would need other choices, and again, for this we use sort of different patterns in the knowledge graph to find things that would be sort of confusing. For example, we get other things that are objects of the used for relation. So we have here losing weight used for being healthier. We have here something else that's used for buying things at store. Maybe we can try to put those as distractors. So then a question would be, what is losing weight good for? Basically, what is losing weight for? And then it's for being healthier, and it's not for buying things at store. So what we did is we basically did this a lot of times. So we created hundreds of thousands of questions like this from CSKG, and we use those to fine-tune the language model. So we call this here pre-training, because it's sort of training that comes before any of the data is really seen. And as I mentioned, we're actually not really using the official training data of the task. So essentially what we do is we take the original language model as is, we pre-train with this bunch of questions, we get a new sort of, let's say, common sense aware version of it. And then we can apply this same model across different tasks. And here's the experimental setup that we are working with. So we work with two different language models, GPT-2 and Roberta. We work with different subsets of the graph. So we work with the full CSKG, but we also try to see what happens if we generate subsets only with, let's say, the atomic graph, or only with the other sort of sources in CSKG. And then, as I mentioned, we work on 5 different tasks, including sort of social reasoning, common sense QA, which is kind of a broad category of common sense tasks. We have physical IQA, which is physical reasoning. We have Vino Grande, and we have ANalyze. So these are all sort of different tasks that people have been playing with. So the first thing that we see is really what is the key thing here. We basically see on this slide that this works. So we see that if we take, let's say, Roberta, and if we pre-train Roberta with our CSKG questions, we get an obvious improvement across all data sets. Sometimes this improvement is really huge, so like 15, 20%. Sometimes it's more modest in terms of like 5% or so. But in general, we see that the improvement is really notable. If we look into GPT-2, which is the other model that we have been working with, here the improvement is still there, but it's sort of more modest. So it seems that there is something in Roberta that allows it to learn more from these questions. The next question that we ask is, how much of this knowledge is really needed? So if we take the full CSKG and all the questions that we generate, is that really better than if we take only the atomic subset or only other subsets of the graph? And here we see that on average, using the full graph is better. So we perform best with the full CSKG on 3 out of 5 data sets. However, we see that on 2 of the others, we have better performance by using individual subsets of the graph. And this is really the interesting thing that we are looking into here. So we see that we basically see that on 2 of the tasks, we know that on these 2 tasks, there is a relation between the way in which data was created and the graph that makes bigger difference. For example, CSQA was created quite tightly in relation to ConceptNet. So this is why actually we are seeing that the sort of ConceptNet++ subset performs really well here. And we see that on social IQA, which is basically has known relation to atomic. We see that in this case, this specific subgraph does really well. It's almost as good as using the full Commonsense knowledge graph. So this basically shows that although in general it's good to use as much knowledge as possible, there is something to be said about the alignment between the knowledge that we train the model with and the actual task that we apply it on. So the takeaways from this first sort of work that we did is that the first part is, yes, you can use a single pre-trained model to learn to perform all of the tasks. Obviously, the performance is not yet as good as doing the fine-tuning per data set, but we are still performing much better than using the vanilla language model. The second finding is that if we pre-train with CSKG knowledge, we are able to get pretty large and consistent improvement over vanilla language models. So we saw that this is in the range of sometimes up to 20%, sometimes a few percent, but still it's consistent and it's relatively notable. And the final finding is that more knowledge helps, but this really depends on the alignment of the knowledge that we use and the task. All right, so let me go on. So what happens in the other work that we did is we sort of take this idea of the alignment between knowledge and the task further. So the good thing about using a knowledge graph in the first place as sort of generator of questions is that we have a certain structure that we can look into and possibly exploit. For example, what we do in the next work is we say, there is part of the knowledge that talks about, spatial things, and there is part of the knowledge graph that talks about utility stuff and temporal stuff. So this is sort of inspired by, let's say, the axioms work. So can we sort of use these different types of knowledge in the graph to basically, can we align these different knowledge types and see what's their role on the final reasoning? So this is our approach. So what we do here is we take CSKG and we try to organize its knowledge along different dimensions or knowledge types. Like the ones I showed before, spatial knowledge, temporal knowledge, something like that. And then once we do that, we try to align these knowledge dimensions in the graph with different tasks. So how do we do the first part? We take a really bottom-up approach, which is different from what actually most people have done in the past. There are other works out there that try to infer dimensions. I think what is sort of different for ours is that we take an approach where we first survey the relation types in these existing sources, and then from there we try to manually cluster them into dimensions. So these are the sources that we looked into. They are sort of quite a broad set of sources. We include common sense knowledge graphs, like let's say ConceptNet and ATOMIC, and others that I already talked about. We have common knowledge graphs, like for example, Wikidata. We work with lexical resources like WordNet or FrameNet, visual sources like Visual Genome, and then also corpora. So here's what we really come up with. So what we do is we take these sources, we take all of the relations they have, and we try to sort of find emerging dimensions in them. And we see that some of the dimensions that emerge are, for example, lexical knowledge. So many sources, for example, ConceptNet or FrameNet, WordNet, talk about sort of these lexical connections between things. So form of one word is a form of another word, or it's a label of another word, whatever. So this is sort of kind of the most boring dimension in a way, because it's sort of this very syntactic knowledge. And then we go more towards similarity and distinctness. So similarity is about things that are either synonyms or are just similar to each other. Distinctness is about things that are antonyms or just distinct. And then we have some of the usual suspects, like taxonomic knowledge, part whole knowledge, spatial knowledge, which actually, so it's interesting that this corresponds to what we see in the work by Gordon and Hobbes. So, Gordon and Hobbes talk about spatial reasoning, spatial knowledge being either about at location, so things is at a certain location, or something is located near something else. And it's interesting that we sort of see these emerging patterns also in these graphs. We have creation knowledge, we have utility knowledge, we have this motivational category about what agents desire and want. We have quality knowledge, so these are properties of objects, comparative knowledge, temporal knowledge, which talks about events and their prerequisites and their effects and causes and things like that. And finally, we have this final category of relational other, which is underspecified knowledge that holds between two different concepts. So you see that actually the table is fairly generally well populated. So if for most of these dimensions, we see that multiple sources actually talk about them. So this is the summary of the dimensions we come up with. We have 13 dimensions in total. And so we don't really claim that these dimensions are universally the best dimensions to go with, or universally correct or anything, but they have a really practical value in this case. And the practical value is that we can take these dimensions and we can take our graph and we can sort of split the graph, but this time not along the sources that it has, but really split it along the dimensions that it has. So basically, because we did already the consolidation work, we can now take our consolidated knowledge graph and say, okay, let's find the temporal relations, let's find the spatial ones, and so on. And once we do this, we can say, okay, can we now generate pre-training data for each of these dimensions and see what is their impact against different tasks? If you take only the spatial knowledge, does that really help the most on the physical reasoning? Or if you take I don't know, temporal knowledge, does that help your social reasoning, and so on? So how do we do this in practice? Well, what we do is really the same old method where we sort of generate questions from CSKG. The only difference right now this time is that we generate questions with one dimension at a time. So we take only temporal questions, only spatial questions, and so on. And here's what we really find with this. So what we find is that we are able to, again, we expect that if we use all of the questions, we are able to perform much better. These are more or less the same results that we saw before. But the interesting thing is what happens if we use a subset of this knowledge that corresponds to a certain dimension. And probably, as one would expect, if you only use the lexical knowledge, we get really tiny improvements. So, we get like a few % improvement. On the contrary, if you use, for example, utility knowledge or temporal knowledge or, motivational knowledge, generally you get way better performance. On the first data set, which is Commonsense QA, we find that using utility knowledge performs better. It even performs better compared to the full set of questions. On the second task of social IQA, we see that temporal knowledge performs extremely well, again, slightly better than using all of the questions. So this sort of confirms some of the findings that we had before, that, in general, if you don't know what to do, using as much knowledge as you can is great. If you have certain indicators to basically do this in a bit more precise way, that might be better. So if you want to solve social reasoning, you should emphasize temporal knowledge and desire knowledge and whatever. And maybe just discard most of the lexical knowledge, something like that. So one of the hypotheses here is that probably one of the reasons why lexical knowledge is not useful is that the language model already sort of knows it. And you can see here the answer to that hypothesis. We see that if we take a vanilla language model, so without any training, and we apply that, and we basically try to answer these questions with it, it already sort of is able to perform nearly perfect on like lexical knowledge, extremely well on distinctness and these other things, but way worse on temporal and quality knowledge. So this, this makes sense with respect to what we saw before. If we train the language model with things that it doesn't know, obviously we can expect that it can get better. And in this direction, I just want to briefly mention that we are working on another way to basically subset the space of questions. And this is work inspired by the data maps method that was proposed last year by the AI2 people. And this idea is basically that we can take the whole data that we want to train our model on, and we can monitor the training time behavior, and we can see, depending on the confidence that the model has in the correct answer, and depending on how variable its confidence is, we can see how many of the questions are actually easy to learn or hard to learn or ambiguous. The hypothesis here is that easy to learn questions would be sort of well known by the model, so we mostly don't need to train the model on those. Hard to learn questions are questions that typically are, or at least often are, mistakes in the data. So they would allow us to identify things that are just bad questions to work with. And the ambiguous questions are supposedly the ones that will give us, the most valuable subset of questions to work with, because these are the questions on which the model is sort of changing its mind along the way. And in our preliminary experiments, we see that, if we take sort of the ambiguous questions and the easy, and 10% of the easy questions, so this is something around like 15% of the data, we are able to get way better performance. Well, sorry, we're able to get better performance than if we use the full set of questions over like 4 out of 5 data sets. So this is encouraging. I mean, this is work in progress, the work with data maps. But what we want to do next is essentially combine this idea of data maps with the idea of dimensions, and see if we can get even better and even more efficient training for our models. So the findings of this part are that basically if we exploit the structure of the graph and identify these sort of knowledge dimensions, we can get to like a controlled adaptation of the language models. Not all dimensions are really informative to the language model. So we saw that, let's say, lexical knowledge is largely redundant, and then temporal knowledge is extremely useful. So there is something to be said there. So we hope that by combining these dimensions with other indicators like the data maps, we would be able to get to even more efficient and effective pre-training of our language models. Okay, so let me spend a few more minutes to just discuss, to just look back and see where we stand. So the research goal that I post in this presentation is how do we build a natural language agent that performs well on all known aspects of common sense? And this is the story so far. So the current, the situation before was that we had many dataset specific natural language common sense agents. So basically we have one version of the language of the language agent per task. The first thing we did is we basically found a method to sort of discard the training data and use the common sense knowledge sources to pre-train the language model with those. The next thing we did is we sort of expanded this to take the knowledge graph, split the knowledge along different dimensions, and then only feed the language model with sort of one dimension at a time and just see what happens. And in this way, we are able to see how the language model reacts to different dimensions, but also sort of understand a little bit how far we are with respect to our goal of having enough knowledge from all of these different dimensions or aspects. So where we stand right now is that, yes, we have a language, we have a single natural language agent that can work on different knowledge, on different common sense dimensions. So the part of the question that we posed or that regards the perform well part is, so here we kind of provide evidence to that one. So what we see is that our single agent performs sort of in between a vanilla language model and the fine-tuned individual language models that we had earlier. So this sort of means that it seems like we are on the good way, but there is still a lot of work to be done, maybe using larger language models, using more complete sources, maybe using different sources of knowledge. So really it's an open question. But the bigger question that I really posed in the beginning of this talk is, how do we get to 2050 sort of earlier? How do we get to these agents that can have enough common sense that we can have them around us, help us with our tasks, help us with our household items, maybe entertain us, whatever. And I think in order to do that, we have to move from having a single natural language agent to a single embodied agent. So I think this transition, even though it's a single word, it really takes a lot of effort. And one idea here is basically, can we do something similar? So can we use common sense knowledge to enhance an embodied agent this time rather than a natural language agent? And let me talk a little bit about how I am approaching this. This is work in a very early stage, so we have no real results here, but we have some ideas that we are working on. So the task that we are looking into here is the embodied QA task, or EQA abbreviated. That is a task that says, can we basically, if you ask an embodied agent in a simulated environment to do something for you, how good that is. For example, one question would be, what color is the microwave, things like that. And the task is restricted to only household environments, so sort of these 12 rooms and sort of 50 different objects that you find in a place. And the task provides this sort of baseline that allows that basically consists of a planner and a controller. So essentially, it's a neural baseline where the embodied agent sort of moves around the environment and has to eventually find the object that it has to answer about, and then provide some answer. So how would this work with a common sense knowledge? If we have a question, for example, like what color is the cabinet in the kitchen, we can ask CSKG, what do you actually really know about cabinets and kitchens? And we see that, for example, cabinet is found on the top of a counter by kitchen, or cabinet is for food, or cabinet is with a coffee maker, or it's above fridge, things like that. So there is obviously some work here to be done to select useful knowledge from this, or maybe generalize over it. But the idea is that we can use this common sense knowledge that we have already stored to somehow somehow generalize, somehow inform the embodied agent how to do these tasks better, maybe give it hints where to look, and so on. So we're looking into different ways to do this, either by sort of expanding the question itself, or by having this dynamic question answering module that the agent would be able to talk with. For example, if it sees a sofa, then it can ask our knowledge graph, and then we can get some indication that maybe you're in the living room, but you need to go to the kitchen. So maybe, I don't know, what's on your left? And so this is really early work, but this is what we are really aiming to do. This is work with people at ISI, people at Bosch, and at CMU. And this is the final slide. So this is another thing that we are trying to do, again, along the same theme of embodied question answering and common sense knowledge. Can we take CSKG and create these sort of embodied environments sort of automatically? Can we create many embodied QA tasks just by following paths in the graph? And here you see one example. One path that we get from, let's say, starting from piano is, piano is located in a drawing room that's part of a house, located near a person. And then it gets a little bit weird that it's made of water that's used to put out a fire. So obviously, this again needs some work. But if we can find these good paths, then we could, after filtering and scoring, if we are able to visualize them, then we can actually teach an agent to perform tasks and see how far the agents go. Obviously there is an opportunity to create a lot of such tasks. The problem is that, the knowledge is really sort of not very rich. So one thing that we want to look into is, can we really do this a little bit better, or actually a lot better, by using some of the more some of the prior work, let's say on axioms, for example, like the one here. Can we sort of integrate all of these axioms that people like, Ken Forbes or Jerry Hobbs have been thinking a lot about in the past? Can we take them and sort of merge them with our graph? And this work is together with Jay, Hanji, and Mayank here at ISI. And with that, I would like to conclude, and thanks everyone for your attention.
Thank you, Filip. Due to the nature of this being a job talk, we decided to open up the Q&A for people so that they could actually unmute their microphones and speak freely rather than just use the chat window. With that in mind, Emilio had his first question, so maybe he could actually ask it in person.
Sure. I mean, I have a couple, but I'm gonna try to be concise since we're a bit running out of time. So I thought that the motivating example that you borrowed from Oren is a bit problematic for a number of reasons. But I should say, obviously, I am in support of common sense reasoning for AI. I'm just playing devil's advocate in some sense, right? So what I wrote in the chat was, you can argue that, the car being misclassified is an issue of a poor computer vision model rather than an argument to require common sense, right? Because there are, when you as a human reason about that situation, you wouldn't necessarily exclude a priori the possibility that there is a car in the pond, right? It could be a toy car sitting on the, the bottom of the pond. It could be a car wreck of someone who, ended up with their car at the bottom of the pond. So there is, like, when you reason about these particular cases, and you can expand to many of the examples that you brought about today. So what is the general argument that you need common sense reasoning in these specialized tasks? And how do you think your models address that general issue? Related to that, when it comes to interpretability of these, I am a little bit curious to ask. You have mentioned many times during your talk, for example, in the first application, things like, oh, it looks like Roberta has something that yields better performance, but we don't know what it is. Okay, so sure, we can put together pieces and come up with a model that does better, but if we don't know really why, we're not able to interpret it, we're not going to be able to understand how this, generalized to out of a sample question and so on. Then what do we learn? So if you can speak about interpretability of this approach. And finally, connected to that, the last question is, I was a little bit surprised that you didn't mention at the end, at least for the future work and so on, anything about fairness and bias of these potential approaches, right? So what happens? I think we all know as a community now that these large language models can be extremely biased, right? How can that be exacerbated or mitigated when you complement the language models with knowledge bases, right? Maybe I'm not expecting that you already have an answer to that, but I think this would be an extremely important problem if you're building common sense AI machines and the knowledge component of the machines is distorting even further their attitudes. So these are three different questions. I don't know you can answer some of them or whatever time allows. Thanks. And thank you for the nice talk.
Thanks. Thanks a lot, Emilio. I mean, I think these questions are great. I actually some of the slides that I essentially moved out of the talk actually address some of these issues. The question about better model, I think it is so it's really possible that the next model will address a number of these issues. I think the fundamental argument is that is the argument of robustness. So I think we see that that models are sort of shifting around. So we are shifting from one problem to another. But what we often see is that even if you're correct, actually, so let's say that this example was that the next model we figure out, there is no water, there is no car, it's something else. Small perturbances of the input really get to trick them a lot. So I think there is something to be said about robustness. And I don't know exactly how to do this, of course. If I would include it, but I think there is something to be said about using a more symbolic approach as a backbone to these. So if we can somehow, for example, one of the things that we see with language models is sensitivity to like linguistic variations or not being able to deal with negation. So if the language model knows that, I don't know, if it knows that elephant is larger than a ball, it might not know that ball is smaller than an elephant. So this is work that Jay, for example, did. So we see a lot of these examples that show these sort of sensitivity to the form rather than the actual content. And I think one way to solve that would be to perhaps think a bit more towards adding other control mechanisms. I think in terms of interpretability and fairness, so interpretability is something that I think we haven't improved upon. So I think that's something that, even though we use knowledge, which has the potential to help us interpret things, our own method specifically doesn't really improve this. There are other methods that we haven't looked into, like, for example, the work by Xiang Ren, which has, graph neural networks. And I think those could be really much better to do this. In terms of fairness, this was one of the examples that I removed actually from my initial motivation. There is an example, with GPT, how, it generates these, it's a well-known viral example about, Muslims, whatever. So I think this is a big problem that we have to address. I personally am not working on this right now. There is really interesting work by AI2, by Yejin Choi on collecting norms and ethical judgments. It's just that it seems like much of the ethics and morals are also a very fluid category. So I think it really requires a lot of thinking about argumentation and stances, it's something that we haven't touched upon, but I fully agree that it's a super important direction to think about.
Great, thank you. And although we're running out of time, I did want to give Ulf the opportunity to ask a question. And for those who have to leave, they're free to leave as well.
All right. Thank you. Thanks, Philip, for a very interesting presentation. If I understand correctly, many of the common sense tests seem to be multiple choice, which of course facilitates evaluation, but it's also somewhat unnatural in the real world. So what would it take to move to high performance on open answers? Are we close, or is there some other important piece missing?
Yeah, this is a great question. So this is something that we have been, that the community actually as a whole has been moving towards in the last year or half a year, towards sort of going from discriminative to generative evaluation, where you can ask a language model something like, I don't know, so what are things that you bring at a picnic or something like that? And then the language model has to give things of arbitrary length. The problem here primarily is evaluation. So we haven't really figured out how to evaluate things out in the open. You could think about, having sort of crowd evaluation that is online, but that is extremely expensive and maybe difficult to implement. And then the automatic metrics that we have, like mostly the machine translation metrics, they don't seem to be, good enough to capture much of the subtleties and the different phrasing that people have and express through language. So this is really where we stand. With that said, I think still most of the newest evaluation benchmarks are actually generative. So I think we are slowly moving in that direction.
Great, thank you. Another question. So I'm sorry, Ulf, did you have other questions?
No, there was this. Thank you. So.
Okay. The other question comes from David Zhang. David Zhang, you're free to unmute yourself and ask a question.
Hi, this is David Zhang. I think I typed the question from the chat. If you read it,
Okay, sure, I can do that.
Okay.
Yeah, so the question is, CSKGs are formed from multiple data models, such as Wikidata, etc. Among these ontology data models, there are many conflicts. How did you align the data set and solve the conflicts? Did you do it manually? Yeah, so this is the part that I entirely left out of the talk, just because of lack of time. We have a paper on consolidating knowledge graphs. Actually, it's called CSKG, the Commonsense knowledge graph. It's linked in the presentation. That explains these. That explains our procedure. I fully agree. It's a really difficult problem because for example, WordNet has a very symbolic approach to modeling knowledge, and then ATOMIC has nodes that look like sentences, and there are all sorts of things in between. So how to consolidate all of this? I think it's still not something that we have fully solved. Our current approach focuses on how to do this for nodes and how to do this for relations, sort of separately. For nodes, we do node resolution in a number of ways that combine sort of manual mappings that people have created, and then also some automatic methods that are based, let's say, on language models and descriptions. And then in terms of the relations, one of the key consolidation that we did is basically the dimension work that I mentioned. And the rest is mostly manual work.
Okay, so Google has Google Knowledge Graph, and I think that there's other companies or institutions, they have their own. So my question to you is, would your approach or your methods are scalable into a very large, for example, handling millions or probably billions of data?
So the consolidation that we did so far has been really meant to work well for the sources that we created, because they're so heterogeneous that I think we haven't really that we basically only just thinking about how to deal with them takes a lot of effort. How to scale this up is a good question. I think one question is really what to scale it up to, because maybe we don't actually have as much common sense knowledge that we want to integrate yet. Although recently there have been other common sense knowledge graphs, but many of them tend to be extracted, let's say, automatically. So perhaps they have a lower quality or maybe more noise in them. So the question is, do we actually really want to do that? And in terms of whether this is scalable, I think some of the approaches are. So I think using sort of language models to compute similarity over descriptions is one method that many people have looked into, and I think this is also what we partially use. So this is one method that would scale. I'm not sure fully how well will it work.
Thank you.
Thank you. Are there any other questions? Especially faculty are free to ask questions. But if not, I would be fine with finishing here as well.
I have small questions about when you're consolidating those knowledge graph to generate training data. Is there any kind of data that interconnected between those two multiple knowledge graph that is useful for training those language model, or you can just generate training data from one knowledge graph and generate for individual training data from individual knowledge graph and combine them, or is there any type interlinking between knowledge graph that you need?
Right, I think there is. So one of the, in general, much of these knowledge graphs are actually sort of disjoint. But what really brings them together often is WordNet. So so WordNet is sort of a popular choice for language models, for knowledge graphs to have a mapping to. So for example, there is a mapping between Wikidata and WordNet that we found, in let's say in BabelNet, and then there is ConceptNet has some of its nodes mapped to WordNet. And then Visual Genome has some of the nodes mapped to WordNet. So this is something that can be used. It's not the full solution, but it's something that can be used definitely to as a training input node. And actually, we've been working on this. We've been working on an approach to sort of disambiguate the rest of ConceptNet, which has its own troubles.
Thank you.
Great, thank you. Are there any other questions? I'm checking the chat window once more. Guess not. And in that case, I think we can end it here. But of course, people are free to ask questions during their respective one-on-one sessions. Okay, great.